and this is the last talk of the session. This is property-agnostic base case extension for scalable verification of distributed systems. And I think Kyle Storey is giving the talk.
There we go. Nice, excellent. Cool. So I'm a big fan of model checking. Model checking is just very helpful to, when you're given a distributed system, you can very easily define the system almost exactly as is given you in the model checker. You can write out your LTL properties to define what things you want to know are true in the model checker. And it's very efficient, very good for verifying safety and liveness properties. However, it only really works on a small system. If you have a large number, it gets computationally complex, it chokes on you. On the other hand, we have theorem provers. You get to use pretty much all of math. The world is your oyster. And you can prove arbitrary things. You can use inductive reasoning to prove properties about arbitrarily large systems. However, getting safety properties and especially liveness properties to prove out in these systems is really, really difficult. So you can see how these pros and cons of these two tools kind of are duals of each other. And if we could combine them, maybe we could get the best of both worlds. So that's what we're going to try and do in hopefully a unique way. And the way what we're going to use as a case study to try this is a system called MyChips. And MyChips is a kind of digital currency. And the way that you can start to think about MyChips is to begin thinking about a barter that involves more than two people. So for instance, Bob, his car broke down. He really needs it fixed. And Cindy is able to fix his car, but she would really like a well dug on her property. It's a lot of work, but John's willing to do that work. But John needs solar panels installed on his house, which happens to be what Bob can do. So you can see if they got together, they could do each other's work and everyone would be happy. So how can we facilitate this exchange? So traditionally, what would happen is Bob, he's up a tree. He really needs his car fixed. He's going to go to the bank. He's going to take out a loan and get some cash. Bob will use that cash to pay Cindy, who will fix the car. Cindy will use that same cash to pay John to dig the well, and John will give that same cash back to Bob in order to install the solar panels. At which point Bob can take it back to the bank, and the bank says, great, but you owe us a little bit of interest. So the question is, can we facilitate this trade without the need for this bank? And the way the MyChip system works is using a series of IOUs. So rather than paying each other directly, we write these IOUs that put all these people in debt to each other. And they just do that as they're needing to make their transactions. And what MyChips does is identify these cycles of debt and arranges so that each person will forgive their successor's debt in exchange for having their predecessor forgive their own debt. So that's kind of what the MyChip system is doing. And that process of forgiving each other's debt, they call a credit lift. And that's the piece that we want to verify. So to get a little bit of understanding of how a credit lift works, we'll just give an example. So the credit lift protocol operates in three phases. The first is discovery, where we're identifying the cycle of debt. That's really hard, and there's no value being exchanged. So we set that aside, and the other two phases we're going to verify. So the second phase is the promise phase, and the third phase is the commit phase, and we'll see that here. So there are three different types of entities that participate in this credit lift. The first is the originator, who is just any member in that cycle of debt who wants to start the process. Then there's any number of relay nodes. These are other members that are in that cycle of debt. And then there's a third special node, this referee. And the referee serves to ensure that all the nodes reach a consensus on whether to forgive the debt or to roll back. So for example, the originator, they want to initiate this process and they're going to send a promise to relay 1. That promise is going to have 3 pieces to it, 3 core pieces. The value that's going to be forgiven, they're also going to specify some timestamp in the future, by which point, if we haven't all promised, we're going to roll back and the promise will be invalid. And then the third is specifying the referee. And this promise serves as a contract between the originator and relay 1 that is made valid when you receive the digital signature of the referee. Cool. So the relay 1 will receive that promise, consider whether they trust the referee to be fair when deciding, and if they like the terms, they'll forward it. Followed by the next relay, and in this case relay 2 is the last one, will send its promise back to the originator. And the originator has seen this promise has come around the cycle, and they believe that everyone's now agreed. At which point, the originator will reach out to the referee, say, hey, I'd like to commit on this lift. And the referee will look at its own time and say, is my timestamp before the given timestamp for this lift? If it is, they'll provide their digital signature. And in this case, they do provide their signature verifying that it's been completed. So at this point, the originator has a promise from relay 2 to forgive its debt. So it's motivated to send the signature to relay 2 to make good on that promise. At which point, relay 2 is also motivated, but has a problem, experiences an error and crashes. So it's not able to forward that signature to relay 1. And relay 1 has received the promise, and according to its own clock, it's well past the timestamp limit. So it's left in limbo. It needs to know what to do. And what it can do is it can reach out to the referee and say, hey, what's the status of this lift? At which point the referee can look in its records and say, oh yes, I know this lift. Here is the signature. So you can see that all the active nodes are able to reach a consensus that we're supposed to forgive each other's debt. And relay 2, if it were ever to become active again, it could also reach out to the referee to find the status. So that's how we're reaching a consensus. So this MyChips protocol, it's defined using a state machine, and it's fairly straightforward to implement it as a Mealy machine model that we can put into our model checker, which we use to spin. I don't want to get into too much detail here, but suffice to say, it's fairly easy to implement in spin. The question is, how can we verify a system that's arbitrarily large? Spin can verify 1, 2, maybe 5 before it starts to choke, but how can we do an arbitrarily large system? It's one with any number of relay nodes. So to do that, we're going to turn to our theorem prover, and as a basis for that, a theoretical basis, we're going to use trace theory. The trace theory was introduced by Dill some 35 years ago in the context of electronic circuits. And what he considered is, when is it safe to substitute one electronic component for another? And the way he went about doing that is considering traces. So for instance, this electronic circuit, you might see the input A change, followed by the input C changing. This is all feasible. Followed by the output F changing, and then the output E changing. That's a possible trace of this electronic circuit. However, if we look and see A change followed immediately by a change on F, just because the way this module is wired, that's not feasible, it's not possible. So what Dill said is, let's just consider these modules as black boxes and only consider the possible traces of inputs and outputs that could happen. Cool. So with that idea of like, when is it a safe substitution, how can we use that to prove these properties for an arbitrarily large system? So the way that we're going to do it, we start with a small system that we can verify in spin and prove the properties on, with just one originator, one relay node, and one referee, the smallest possible system. And then we're going to look at the relay node and put a black box around that and consider what could fill this role. Now, of course, a relay node could fill this role, but the question is, can we put in here a chain of n relay nodes and have it fill this role, be a safe substitution? And if we can prove that, then we can say that for a large system, the properties we proved on the small, because it's a safe substitution, the properties continue to hold. So that's the approach. Now, it turns out it's very difficult to prove this directly in the Mealy machine model. It's very tricky to prove. So what we're going to do is we're going to use a different representation. So we're going to use a partial order representation that's essentially just a series of rules that define the input and outputs and the traces of events that we could see. Cool. Sorry, I'm a bit lost. Okay. So, I think I got my slides misordered. Where am I? Okay. So, for an intuition of how this proof is going to work, we're going to start with our base system that we are able to verify using our model checker. We'll prove all the properties we're interested in. Then what we're going to do is, Okay. Then what we're going to do is take our relay node. I'm going to go back. I'm sorry. Okay, so there are 3 core lemmas that we're going to need to be able to prove this inductive proof. The first is the base case, which we can prove with our model checking. The second is conformance equivalence of a chain of n plus 1 relay nodes to n relay nodes using our partial order definition. In our math, we use this B for black box. It's our black box definition. And then the third piece we're going to use is conformance equivalence of our black box definition to our original Mealy machine definition. So if we have these 3 things as lemmas, we can show that the properties we care about extend to an arbitrarily large system. All right, so to start, we have our base system, which we've proven our properties on that we care about. Then we're going to use our lemma 3 to show that it's a safe substitution to replace our relay node with our partial order definition of our relay node. Then we're going to use our lemma 2 to show that a chain of 2 of these partial order definitions of the relay node is a safe substitution. And we know if that's a safe substitution, the properties continue to hold for the system. We're going to use our lemma 3 one last time to convert us back to the Mealy machine model, and that's our inductive step on our proof. Okay, so this is a lot of things to believe, but if we can show these 3 lemmas are true, then that gives us all we need to prove that the system continues to hold, the properties hold as the system grows large. So the first case is fairly straightforward to implement in spin. I don't want to go into too much detail, but there are 4 properties that we cared to verify. The first is that we are not left in limbo hanging forever, that we eventually get out of the pen state for all of the nodes. The second is that if any of us believe that the lift has committed and we've forgiven debt, then everyone believes that the lift is forgiven. Third, we say that always eventually we're going to we're saying that nobody's harmed. Their balance, the change, the amount of debt they've forgiven versus the amount of debt they have, is typically 0, but we do allow for it to be greater than 0 in cases where some nodes go inactive. And then last, we say that for all active pairs of nodes, they agree on their change of balance. So these are the 4 properties we care about and we prove. And in our model checker, we can very quickly evaluate that. It takes some 16,000 states, 172,000 edges, and on my machine it took 10.5 seconds to prove that. So that proves our first lemma. So we'll move on to the next, this conformance. So the idea that a larger, more complex system can conform to and be a safe substitution for a smaller system can be unintuitive. But what makes this possible is this idea of projection. And the idea is that if we have, it essentially boils down to hiding the internal details, the complexity of the internal of this component. So if we have a system, for example, that has a chain of 3 relay nodes, we have 0, 1, and 2 in here, and we want to consider whether it's a safe substitution for 2 relay nodes, what Dill's work allows us to do is through a series of renaming and hiding things, we can reduce the alphabet of events of the larger system onto the smaller system and essentially just remove those events. You can look at Dill's work for how that works. But that's what makes it possible for this larger, more complex system to conform to the simpler system. But that doesn't solve everything. What we still need to be able to prove is that that projection doesn't change our partial order rules, that our partial order survives that projection. Now, this can be pretty tricky, and it really shows the power of our interactive theorem prover I used, Coq. There's a lot of edge cases that are really tricky, and it is able to enumerate all of those cases and force me to deal with them. Now, the first 7 are fairly straightforward to prove. The last one is the most difficult. This all receives causal. This is the idea that if you've received a message, it must have already been sent. And you can imagine that if you have a system with, say, 3 nodes, you have node 2 sends a message to the originator, node 0, right? So node 0 has received a message, but when we project the system, that send from node 2 gets projected out and gets lost. So it appears that this node 0 received a message and it wasn't causal. However, we can show that for all valid system, there exists a node 1, in this case node 1, that sends a message that would have gone to node 2 that can wrap around. So there's some tricky cases. It shows the power of our theorem prover that we can look at each of them individually and check them out. You don't have to trust me. You can go and check the source code. It's a machine-checked proof. For some road markers along the way, the top-level proof is larger conforms to smaller, and we write it in this way. It's for all traces, it's an ordered list of actions. If that trace is valid for a system of size n plus 1 and n is greater than 1, then that implies that when you project that trace onto size n, it's valid for size n. And this is not quite exactly what we're looking for as far as what Dill would have written for it, but there's a theorem in the paper that shows that this property implies the conformance that we care about. So our theorem prover, it's not a pretty proof, but it is machine checked. It's 24 lemmas and theorems. It's almost 2,000 lines of code, and it takes about 8 seconds for that proof script to verify.
So you're missing one more time. How long did it take you to write it?
That's a very long time. We're talking months, probably 9+ months to write it. So it's very difficult. It's manual effort for sure. Cool. So that's our second piece, this conformance of n plus 1 relay nodes to n in this black box model, but we still have to show we did this representation change. We need to show that that representation change was a safe substitution. So we can do that using conformance equivalence, saying one is a safe substitution for the other and vice versa. So we can take this and do a few simplifications. First, the alphabet of events for a single relay node is the same, whether it's using our partial order definition or using the Mealy machine, so we can just drop the projection, they're equivalent. And we can consider the possible traces of events in our black box model versus the possible traces of events in the Mealy machine model. And we need to consider both sides of this disjunction, and we can do one at a time. So this side, we say that all the possible traces in our Mealy machine model is a subset of the possible traces in the partial order, right? So with a little bit of Boolean algebra, we can show that this is the same as saying there does not exist a trace that violates the validity rules, the partial order, right? Which happens to be something that a model checker is very good at checking for us. I'm a big fan of model checking, and we go ahead and do that. And it takes a little bit longer as far as computational goes, but 24 seconds, we're able to prove that there doesn't exist a trace that violates these partial order rules. So that gives us this half of the disjunction. We still have one left, and I'll tell you that this we've satisfied to our satisfaction, but it's not quite the same level of rigor as the others. So we're trying to say that the partial order is a subset of the possible traces of the Mealy machine. Now, we consider the traces of events that are possible in the partial order. And this trace of events is actually infinitely large. There's some cycles where a node can reach out to the referee, and the referee says, oh, actually, we don't have a signature yet, but we haven't reached the time limit yet. So just pend, ask again later. And this could potentially happen an infinite number of times. That's a loop, right? So the set is infinitely large, so we can't evaluate every single one. But this MyChip system is designed to be idempotent. So if you receive a message once, you reach the same state whether you received it once or multiple times. So what we can do is divide all the set of traces into equivalence classes and then pick a canonical member of that class where each trace has each type of message at most once. So we can break that up. There's 9 equivalence classes that we've identified. And the question is, are these equivalence classes present in our Mealy machine model? Which again, I turn to model checking for that. Now, for these 9 cases, we considered each of them. They're very quickly discovered, some more quickly than others. And to find a witness trace for each of these equivalence classes, it took our model checker some 28 seconds. Cool. So that proves the first one, the second one, and the third one with, we have high assurance that this third lemma is true. So given that, that shows that our inductive argument, we have our base case, we have our inductive step, that shows that the properties we care about extend to an arbitrarily large size. Cool. So we extended the model checking results using an inductive proof. And we did that using Dill's trace theory and conformance in 2 unique ways. The first is to prove the inductive step, and then the second is to transition between 2 different representations of the system. Show that's a safe substitution. What's really nice about this method is you can prove any properties you want using model checking, and we don't need to know about them for our inductive proof. The inductive proof doesn't consider what properties we've proven, which means that if there's anything else we'd like to prove extend to this large system, all we have to do is check our small system. And we've shown that the properties continue to hold. So that's a really nice feature. And I'd just like to say that for the 4 properties we looked at, given some assumptions that in the MyChip system, those 4 properties hold for an arbitrarily large number of participating nodes. That's that. Yeah.
So, wait. Oh, I'm online. Right. So for the very interesting presentation, very interesting combination, by the way. For the third property, the third part of your proof you had, why do you need to establish both directions? Maybe for safety properties, one of the directions is enough, right?
Yeah. So that is unknown, right? It's like, it seems like maybe we don't need it, but how can we prove that we don't need it? So maybe there's a weaker kind of equivalence that we could have that's maybe not this conformance equivalence that would be sufficient, right?
I mean, so typically for an abstraction would be enough for safety property, right? Mm-hmm. So if you check the safety property on the abstraction, you're okay. Mm-hmm. So I would think R less than or R in your partial order less than equal to B should be enough for at least for safety. Maybe not for other kinds of properties, but okay.
Right. Yeah, that's a good point.
So here, so for the last conformance equivalence, you consider the inclusion of the traces, right? Mm-hmm. So is there any situation that you need to consider like a stronger conformance equivalence? Not only the traces, but probably for every several steps you need to be seen.
Yeah, so that's a good question. So the idea, I think it comes down with what Dill's work is giving for us, is that by showing that the possible set of traces is a subset, that's just allowing us to show that it's a safe substitution. Really, we're not considering the properties for that case. It's just a means for showing that we can substitute this larger system.
I see.
Does that answer your question?
Yes, but what I'm thinking about is it possible that your system behavior can be so complicated such that you only require the inclusion of the trajectories cannot really guarantee the safety or guarantee the similarity?
I suppose there are some things, like for instance, timing, right? If you're timing reliant, then this is not going to work for you.
I see. Yes.
There might be other properties,
Exactly.
right?
Yes. Thank you.
Any other questions?